Today we're going to start Chapter 8. We're going to take a look at chemical bonding and how we can represent chemical bonding by the electrons that are being exchanged or the electrons that are being shared during the course of that chemical bonding and that reaction. A few announcements to get us started. Exam 3 is Thursday, October 29th. It'll be open for 24 hours. It'll be the same format as Exam 2. Practice exam is set for Tuesday night. That'll be due. The review session, I'll also have a review session Tuesday night, 8 to 9 p.m. I will also have a review session Wednesday night just for the asynchronous class, the M045. Exam 3 covers chapters 6 and 7, so 25 questions, multiple choice, some calculations, some fill in the blank. And there are 2 questions that are set for you to submit your work as a PDF. It's only set up to take your work as a PDF. So I've got 1 question posted on the discussion board right now in Top Hat for you just to practice that and see what that looks like. But try that, give it a try before the exam so you know what to do during the exam and I don't get 1,000 emails during the exam asking about that. So give it a try on the discussion board. Answer that question by uploading a PDF of your work, handwritten work. All right, so last class we ended off talking about ionization energies, electron affinity, and talking about when metals and nonmetals react, what happens. And we talked about how metals tend to have a lower ionization energy. And so why do metals tend to form cations? Metals tend to form cations because of this low ionization energy. It's easier for metals to lose electrons, right? They have a greater tendency to lose electrons, whereas nonmetals have a higher electron affinity, so they're more likely to gain electrons. And so when a metal and a nonmetal react, right, when we combine a metal and a nonmetal, we form ionic compounds. We form ionic compounds because metals have a low ionization energy, which makes it easy for metals to lose electrons. Nonmetals have a high electron affinity, meaning they want to gain electrons. So when a metal and a nonmetal react, right, the metal wants to lose electrons, and the nonmetal will gain those electrons. What about a molecular compound? So a molecular compound is held together by covalent bonds, right? So molecular compounds form between nonmetals reacting with nonmetals. When 2 nonmetals react, why do we form a covalent bond, right? Whereas when a metal and a nonmetal react, we get an exchange of electrons and we have an ionic bond. Well, nonmetals have a high ionization energy. And that makes it harder for a metal to lose an electron. Making it harder for a metal to lose an electron. As a result, right, nonmetals, when they react, nonmetals are more likely to share electrons. And that's a covalent bond. So for today's lecture, we're going to look at ionic bond formation. An ionic bond is a chemical bond formed between the electrostatic attraction between two oppositely charged ions, a positively charged cation and a negatively charged anion. We form an ionic bond between the reaction of a metal and a nonmetal. So how do we determine how that ionic bond forms, right? We know by looking at the electron configuration and thinking about the electron affinity and ionization energies that metals will lose enough electrons, right? Basically all valence electrons to obtain noble gas configuration. Right, becoming isoelectronic with a noble gas. Remember, isoelectronic means same electron configuration as our nonmetal. Nonmetals have high electron affinities, so our nonmetal will gain enough electrons to become isoelectronic with a noble gas. Our metals will lose electrons, our nonmetals will gain electrons. Both react in a way to become isoelectronic with a noble gas. And so here's that reaction to form sodium chloride. I have my metal, which is sodium. Sodium is right down here, and I've got one valence electron. My nonmetal is chlorine. Chlorine has 7 valence electrons, so when it gains one more electron, it'll be isoelectronic with argon. When sodium loses its 1 valence electron, it will go from 11 electrons to 10. It would be isoelectronic with neon. So sodium loses that electron, chlorine gains that electron, and then the next step is that ionic bond formation. We get the electrostatic attraction between the positively charged sodium ion and the negatively charged chloride ion. So let's take a look at that with respect to the electron configuration and exactly what's happening. Because ultimately what we're doing is getting a transfer of electrons from sodium to the chlorine. But let's look at that in terms of the configuration, right? Sodium would be neon 3s1. So sodium losing an electron would just become neon plus 1 electron. Let's look at the configuration of chlorine. Chlorine is neon 3s2 3p5. Remember, I can hold a maximum of 6 electrons in my p orbitals. So when I add in that extra 1 electron, the electron that came from sodium, that sodium lost, that extra electron will fit into the 3p orbital, giving me the electron configuration of neon 3s2 3p6, which is isoelectronic with argon. Both of these react in a way to obtain noble gas electron configuration. Both of these react in a way to obtain 8 valence electrons in their outer shell, also known as an octet. Sodium does that by losing its 1 valence electron, obtaining noble gas configuration. Chlorine does that by gaining the 1 electron, right, going from 7 valence electrons to 8 valence electrons in its outer shell. Both end up, after the reaction, both end up with 8 valence electrons, or a full octet. We can represent the exchange of an electron, or we can visualize the exchange of electrons during the formation of an ionic bond using electron-dot diagrams, Lewis electron-dot symbols. And they're essentially a representation of the valence electrons of the valence electrons around an atom where a single valence electron is represented as a single dot. So sodium has one valence electron, and that's what we've indicated right there. Magnesium is group 2, 2 valence electrons, so 1 and 2. Aluminum is group 3, 3 valence electrons, 1, 2, and 3. Silicon is group 4, so 4 valence electrons, 1, 2, 3, 4. Phosphorus is 5, so 5 valence electrons, where each of those dots represents one electron, right, all the way up to argon. Argon is our noble gas, so it's going to have the full octet. It's going to have a total of 8 valence electrons. So these Lewis electron dot symbols, that's all they do, is they represent the number of valence electrons that each atom has, and it helps us visualize during the course of a reaction how many electrons do I need to lose or do I need to gain to obtain that full octet, that full outer shell of 8 valence electrons. And so let's take a look at the example of magnesium fluoride, the formation of magnesium fluoride. Let's use Lewis electron dot symbols to help us understand and demonstrate the reactions taking place and what is actually taking place within that reaction. So for magnesium fluoride, I'm going to have magnesium. Magnesium is neon 3s2. So magnesium has 2 valence electrons. Fluoride is helium 2s2, 2p5. So fluoride has 7 valence electrons. So I'm going to draw the Lewis structure for both of those. My 7 valence electrons on fluorine, right? 1, 2, 3, 4, 5, 6, and 7. Do the same 7 over here. 1, 2, 3, 4, 5, 6, and 7. So when magnesium fluoride reacts, magnesium's going to lose 2 electrons to obtain a noble gas configuration, right? It'll obtain the configuration of neon. Each fluorine wants to gain 1 electron. So how this reaction takes place, magnesium is going to lose 1 electron to fluorine. It's going to lose another single electron to this other fluorine. And so I'm going to form magnesium 2+. And then if I take a look at the fluorines, right, each fluorine had 7 electrons going into the reaction, 7 valence electrons going into the reaction. And here's my 1 electron from magnesium, right? I color-coded it in blue. That's the magnesium electron that was transferred. And here is my magnesium fluoride. Magnesium 2+, because it loses 2 electrons, each fluoride is -1. And now I can form an electrostatic attraction between the negatively charged fluoride and the positively charged magnesium. But we can use that Lewis electron dot formula to represent the valence electrons that magnesium has to lose, right? Magnesium has 2, so each fluorine, right, wants to gain 1 electron. That means I can accommodate 2 fluorines around that central magnesium. Because magnesium loses 2 electrons, each fluorine would like to gain 1 electron, right, allowing for 1 magnesium to 2 fluorines for that formula. So now we need to think about, okay, I can represent the electrons, but why? Why do magnesium and fluorine react? Why do they react and come together to form a bond in the first place? And in general, things react and come together to form a bond because, right, we need to be lower in energy. So the ionically bonded compound needs to be lower in energy than the individual ions. And that means, right, we always want to go downhill with respect to my energy. So most of the bonds that form, they bring us to a lower energy point. And that means we're going to need to release energy, right? Energy should be released when an ionic bond is formed. So let's take a closer look at that formation of sodium chloride and understand the energy involved with each step of that process. The first step is the ionization. I need to go from sodium to sodium +1, right? I need to remove one electron from sodium so that I have an electron to exchange. That is 495 kilojoules per mole. So that first step is endothermic, all right? I have to put in 495 kilojoules per mole of energy. So far, the first step has taken us in the wrong direction, right? We want to go to a lower energy point, and right now we're going up to a higher energy point. The next step is the electron affinity, and that's when chlorine gains an electron. So chlorine has an electron affinity of negative 349 kilojoules per mole. That is exothermic, so that means I'm going to release 349 kilojoules per mole of energy when that chlorine gains the electron. So now let's look at both of those steps together. Here's my ionization energy. I have to put in 495 kilojoules. Here's my electron affinity. When I give that electron to chlorine, it releases 349 kilojoules. So overall, right, my change in energy is a positive 146. So overall, that means we would have to add in 146 kilojoules of energy for this reaction to occur, and yet it needs to be lower in energy. So maybe we're missing something in this calculation. That positive number, that positive 148 kilojoules, means that reaction would be endothermic. If you go to the lab and you mix sodium and chlorine, if you mix elemental sodium with chlorine gas, you will produce an extremely exothermic reaction. And yet on paper, we've calculated that the reaction should be endothermic, that the reaction should require an input in energy. Yet if you were to mix those two together, you would get a very exothermic reaction. So clearly, we're missing something in our calculation. The energy that we're missing, the step that we're missing in our calculation is the lattice energy. And that's because both of the steps we looked at, the formation of sodium all by itself, the formation of chlorine all by itself. But what's happening in reality is that sodium is forming, that sodium cation is forming in the proximity of the chlorine anion. So the step we're missing is the lattice energy, and that's the energy released by bringing together two oppositely charged ions to form an ionic bond. Right, and this is influenced by the charge on each ion and the distance each ion is apart. And we can see that here. So I wouldn't ask you to have to use this calculation, but this is where we get an idea of our law of attractions, is that this electrostatic attraction equals our constant times charge on each of those ions divided by my distance. So as charge increases, right, that's pretty easy to see. As charge increases, my electrostatic attraction increases. However, as distance increases, if distance gets larger and larger, think about this as two magnets. As you move two magnets farther and farther apart, that attraction between the magnets decreases, right? Or we could go the opposite direction. If I were to decrease that distance, right, as distance gets smaller and smaller and smaller, I bring those two magnets closer and closer together, my electrostatic attraction increases. And so here's the energy that we didn't take into consideration in our calculation, the lattice energy, the energy that's released by bringing together a positively charged sodium and a negatively charged chloride ion. The two trends with our lattice energy, right? So in general, lattice energy increases with increasing charge on the ions. And lattice energy will decrease as the distance between ions increases. And so let's just take a look at the first one. Energy increases as the charge increases on the ion. So if we go from sodium, which is +1 chloride, to magnesium, which is +2 chloride, right? We go from 700 kilojoules per mole to 2300 kilojoules per mole. We see a large increase in energy. The only thing that was different was that sodium is +1, magnesium is +2. So as charge increased, the lattice energy increases. The next thing, let's look at our radius, our distance between those charges, and let's keep all the ions the same. So let's look at lithium chloride, sodium chloride, potassium chloride, and cesium chloride. So all four of those have a +1 charge, and we have the same anion. But if we go down the periodic table, we get an increase in ionic radii. So lithium is the smallest, and cesium would be the largest. So with lithium chloride, those two charges are as close together as possible, and we see a large lattice energy. As I get to sodium chloride, sodium's a little bit bigger, moving those charges farther apart, a decrease in energy. Potassium's a little bit bigger, moving those charges farther apart, and then cesium is even larger, moving those charges farther apart and further decreasing the lattice energy. So here are our three steps now, right? I've got sodium and I've got chlorine. The first step is the ionization energy of sodium. I take that electron away from sodium to form a sodium cation. The next step is my electron affinity of chlorine. I take that electron and I give it to chlorine that is exothermic, and I release energy. So this is where we stopped our first calculation and saw that we were still endothermic and saw that we must be missing an energy component to this process. And I hinted at that when I mentioned we just looked at the formation of these ions separately and individually. But what happens when they react, when we get this exchange of an electron, they react in proximity to each other, and they're going to come together and form an ionic bond where the positively charged sodium will help stabilize the negatively charged chloride in this electrostatic attraction. And that's the lattice energy that would be released when these two come together, when sodium comes together with chloride to form a solid sodium chloride. And once we take into account the lattice energy, now here's my overall energy level. Now I'm an overall exothermic process, and that matches our observation of this reaction in lab.